This is a special edition of Transcast, coming to you from the Metrans Transportation Center. I'm Matt Kaplan. Late last year, Metrans marked its 10th anniversary of service to the transportation sector in Southern California and beyond. Author and structural engineer David Billington helped us celebrate. Billington is the famed author, teacher, and structural engineer who has shared his 60-year love of structural design with thousands of admiring students at Princeton University. He was named one of the 5 top civil engineering educators over the last 135 years. His many books include Power, Speed, and Form, Engineers, and the Making of the 20th Century, written in collaboration with his son. It was this book that formed the basis of his Metrans keynote address about transportation and innovation. Hours later, David sat down with me at USC to talk about his work, his philosophy, and his undying enthusiasm for the beauty that can be found in structural form. David Billington, thanks very much for joining us for Transcast, and also thank you for a really fascinating and enthralling, I would even say, address last night for the celebration of the 10th anniversary of the Metrans Transportation Center.
Thank you.
What I'd like is about 2 hours with you to talk about the history of technology and engineering in our society and elsewhere, and what it has meant to the growth of civilization. But they're not going to let me do that. And so, working partly from my notes and partly from the extensive writing about you and by you that can be found online, I want to maybe start with this intersection of art and engineering that you talked about last night, and why that's so important to you.
Well, it came to me through structural engineering. I'm a structural engineer. I'm actually a practicing professional structural engineer as well as an academic, and I became acquainted with the idea of the structural engineer as artist while I was teaching architects. I normally teach just engineers, but I was teaching a course to architects, and they were very unhappy with what I was teaching. They came to me after several years of this teaching, and they said, we like you, we think you're a good teacher, but we hate what you're teaching. And I said, well, I was a little bit taken aback, you might imagine. I had carefully prepared all I was teaching. And they said, well, all we get from you are stick diagrams and formulas. Why can't we study structures through looking at beautiful things? Now, that had never occurred to me, nor to any other structural engineer that I knew about in teaching. And so they showed me pictures of 2 engineers in a big book called Space, Time, and Architecture, a famous architectural book by Siegfried Giedion. And one of the persons was Gustav Eiffel, and the other was Robert Mayer. They were beautiful-looking things, and I thought that was a reasonable request, but I could find no documentation anywhere in the literature about these people as engineers. In other words, how could I teach engineering through this? So I began doing research in this, and that led me to have a conference in 1972 on Robert Mayer, the centennial of his birth, and invited a series of people, and these people all talked about the influence Mayer had on them, and they also talked about their own ideas, which included a strong aesthetic motivation. And I realized then there was suddenly a tradition. There was suddenly a possibility of giving a whole course. So in 1974 I began to do that. And it was not a question of any kind of intersection or any kind of add-on. These people were thinking fundamentally about structural design and seeing in it the possibility of making new forms that were aesthetically driven, but still in a strong discipline of engineering, namely the ethos of engineering, which is don't waste materials, the ethic of engineering, which is don't waste money. So under this strong discipline, they still found the room to make choices which were aesthetic.
That's it. Discipline and choice, which I thought was one of your most interesting themes last night.
Yeah, that's right.
Because you said that engineers realize that even following the strict discipline, there is always a choice. There are always choices to be made that will arrive at a good solution.
And also bad solution. You can come up with a marvelously ugly work by still being within the discipline, but you can also end up with something that isn't ugly. So it was this that fascinated me and made me begin to study. And the first thing I did was to go to our art museum, the Princeton University Art Museum, and say, I want to put on an exhibition of engineering art. And they were sort of strange idea, they thought. But I brought them some pictures of Maillart's things, and they agreed. And so we began. And in the 1970s, we held 5 exhibitions in the art museum. Some of them began to travel. And then I stopped doing that because I thought I better write something about this and think about it and do more scholarship. And then in the 21st century, we've now held 2 exhibitions, one in 2003 and one is just started now, just opened a couple weekends ago. And so these are exhibitions that portray engineering, structural engineering, but the important thing is that the engineers who saw themselves as artists were also the best in the purely technical sense. They were the most innovative. Mm-hmm. They were not a bunch of sort of frilly guys on the fringes doing fancy things at all. They were making important innovations in structural engineering that had nothing to do with aesthetics to begin with, but then they would make them have something to do with aesthetics.
What is it, do you think, about a truly great work of engineering that can speak directly to your soul, to your aesthetic sense? We were talking last night about a wonderful bridge which you've seen on Interstate 15 here in California, which, looking at that bridge, can almost bring tears to my eyes, like watching a DC-3 fly over us from the Long Beach airport.
Yeah. Well, I think that there's a difference between those two.
Yes.
And the difference is the fact that in the Lilac Road Bridge, there was a conscious sense to make an aesthetic design. That the chief engineer, whom I knew quite well in California, Arthur Elliott, who didn't make designs himself but supervised and forced his designers to do something aesthetic as well as within a discipline, that was possible to do. But with the DC-3 and with other objects like that, an airplane doesn't dare do something. An airplane designer doesn't dare do something for aesthetic purposes. They do something always for purposes of the technique. And the DC-3 was, of course, a streamlined machine, beautifully designed, but as far as I can tell, not with an aesthetic motivation. It looks beautiful. There are a lot of things that are beautiful without being art. A sunset is beautiful, or certain kinds of buildings, certain kinds of machinery, all kinds of things can be beautiful without having an aesthetic motivation associated with them. So what has to be, for art, it has to have an aesthetic motivation. The designer's motivation has to be there. Otherwise, it's just accidental.
There's another big difference that you pointed out last night between a DC-3, which is a machine, and a structure like that bridge. In fact, you said, let's see if I can remember the order again properly, structures, machines, networks, and processes.
Perfect. You get an A+.
Thank you very much. That means a lot to me. And
to me, too.
You did a great job of showing how works of engineering, I suppose you could say, seem to fall into these categories.
Yes. Well, it was something that I evolved sort of slowly. I started out giving a course in structures, and then I got a lot of flack about that. They said, well, that's a small part of engineering. There are lots of other parts, and machines are very important. A lot of people, a lot of philosophers and people like that who comment on engineering think of our society as a machine society. So I then introduced a course called Structures and Machines. And the difference that you're referring to is that the structures are normally custom-made. They're made for one location usually, and they're made so they do not move. If a structure moves, it's in trouble, like the famous Tacoma Narrows Bridge. Moved too much.
That famous film of it tearing itself apart.
Whereas a machine, and by machines we're always referring to prime movers. We're referring to a prime mover like an automobile or a power plant or things like that. And in that case, they have to move. So if the car on the bridge doesn't move, it's in trouble. If the bridge underneath the car does move, it's in trouble. Mm-hmm. But the two need each other. Most bridges built today would make no sense without automobiles. And most automobiles would have a terrific difficulty traveling around without bridges. So there's these two complementary sides, complementary objects of technology, of engineering. And then there are systems of engineering, which are not just objects but systems. And those are the network, in which you send something out into the network, and at the other end you expect to get the same thing back.
Like the power grid.
Like a power grid, like a telephone line, like the old telegraph with messages. And so it's a network, it's a system through which things are not supposed to change. A process is just the reverse. A process is something through which things change, like a blast furnace is the oldest one, where you put in iron ore and you put in coke and you heat it all up, maybe with limestone, and you get something quite different out. You get not iron ore, which is useless normally, but you get iron, which is tremendously useful. And the same thing with oil refining. You take this black stuff and you put it in a refinery, and you can get out of it various things: kerosene, gasoline, you can get heating oil, you can get tar. All these things can be separated out, and they're quite different than what goes in.
I think it's safe to say you have a special love for bridge building?
Well, I have a special love for two things in structures. If you leave my wife out of that, because that's the special love of everything. But the special love is for bridges, yes, and the second thing is for thin shell structures.
Mm-hmm.
These roof-type structures that are made out of concrete but are very thin and very durable, those are the two things. And I have written a lot about both of those things. And they fascinate me because they show the limit you can go to make things both beautiful and safe and economical all at the same time. That's the attraction for me. And we can portray these things in art museums. That's what we've done, those two types of things.
It didn't occur to me until listening to your talk last night how incredibly dependent this region, Southern California, is on bridges. Because we all think of our freeways, but really what makes the freeway practical? The bridge.
Yes, you have lots of bridges. It goes over bridges, and then roadways go over the freeway. Yes, that's right. It's you take the bridges away, and you find yourself back in the 18th century.
Uh-huh.
You have Fords
Uh-huh.
and other things like that. But it's very
That's
different.
a Ford with a small f, not
yes,
a
Ford
large
with
one.
a small f. That's correct. Mm-hmm.
You talked about some of the great bridges, not just in this country, but a great deal about the bridges in this country, and how in many ways they enabled, well, I don't know about the Industrial Revolution, but they certainly enabled the growth of this country as they now support the commerce of this country.
Yes. A good statement. I will remember that. You're doing very well, young man.
Thank you.
Not at all. I think that's a very good statement. And the only thing I would add is that in the 19th century, the people from Europe came to the United States to see innovations in bridge design. But in the 20th century, it changed. It reversed itself. We have to go to Europe. In fact, that's what I first met the study of bridges, just like I first met my wife, when we were studying together in Belgium. And Belgium had lost all their small bridges. They have nothing but small bridges anyway, but they lost them all 3 times during World War II. You know, the Germans swept in, the Allies swept them back, the Germans came back. Every time they blew up the bridges. So they developed very good and innovative ways of building small bridges, and that was what I was studying over there. And so they developed something called pre-stressed concrete, which then was brought to the United States, an innovation both in Belgium and France. And I had learned that over there and was able to design a lot of things like that when I came back, because not many Americans knew that type of design. And so, but then in my further studies, stimulated by these architects, I found that the bridges, particularly in Switzerland, were spectacular. And they were due to actually 2 designers, really 3 designers, one of whom left as a young man and came to this country and ended up designing all the big bridges around New York, starting with the George Washington, ending with the Verrazzano. And he was named Amann, and he was the greatest designer of steel structures, steel bridges, that the century knew. And then The concrete bridges were designed in Switzerland mostly by these engineers there, Maillard and then Christian Men. Those are people we have to learn from because our innovative capacities in bridge design didn't keep pace with Europe after World War II, and we have been importing from them. And I'm hoping that by teaching about that, we can re-stimulate the bridge world in this country to more innovative designs.
When people talk about the infrastructure of the United States and that it is sorely in need of renovation, a lot of that attention seems to be on bridges. How do you feel about that?
Well, it is. It's on bridges because it's very spectacular when a bridge fails and kills people, because people take bridges for granted. I mean, traffic accidents kill thousands and thousands more than bridges do that fail, but somehow a bridge that fails, rather than an accident of a car, grabs attention because that is more or less taken for granted. That's something that should never fail. And they're right, it should never fail. And so it has grabbed attention, but it doesn't stay very long. That's the trouble. The bridge in Minneapolis that failed, the most recent one, killed 13 people. Well, that's a terrible disaster, but of course, in another country, a bridge like that could have failed and probably, or in the 19th century, we had bridges that failed and killed lots more people than that. First of all, that was a badly designed bridge, and secondly, it was not a well-maintained bridge. And those are issues that we now have to face with the infrastructure as a whole. I mean, the infrastructure is composed mostly of issues relating to water, issues relating to power, and issues relating to transportation. That's the way infrastructure usually is defined. And bridges are, of course, part of transportation. So, as you said before, we depend on that for commerce and all kinds of things, like we used to depend on the railroads.
Do you draw a distinction between great works of engineering in the private sector and in public works, as you called them last night?
Yes, there's a very big distinction between innovation in private industry and innovation in public works. Innovation in private industry can respond rather quickly because they have a lot of freedom. They're constrained by their shareholders or things like that, but they can respond fairly quickly to the market and to the issues having to do with profit. So that when they see a possibility for a new product or a new idea, it can be brought in fairly quickly. I mean, when Thomas Edison, for example, one of the first great pioneering engineers in innovation, when he saw the possibility of competing with gaslight in New York City by using electricity, he began working on it somewhere around 1878, and by 1882 he had produced the first working power plant, power network in New York City, cleverly nestled into Wall Street where he could raise the money for it. But it could be done fairly quickly, whereas in public works, you normally have to go through a political process in order to get public works approved. The prime example is the Katrina business, is the stuff at New Orleans. Everybody knows New Orleans is subject to these terrible floods, and it is largely unprotected against the highest floods. And yet nothing is getting done. Hardly anything is getting done. When Gustav showed up last month, the Corps had to admit that they were not ready. They hadn't been able to. It wasn't the Corps' fault. They hadn't been able to work the way they should have been able to work following the Katrina disaster. So in private industry, the process you have to go through is essentially an economic one, where in public works, the process you have to go through is essentially a political one. They're both social processes, but they're quite different. And in a democracy, I mean, if you're in a dictatorship, of course you could get things done quickly if you're willing to pay for that. But if you're in a democracy, since we have freedom, you means a lot of people have freedom, and they're going to object to things, and they're going to be a lot of debate about things, particularly when you have nowadays the environment. You have environmental impact statements, which seem to take a very long time to deal with. And so you have these processes, which in the end are a product of democracy, and that's why it makes it longer.
Dictatorships, the trains run on time and the bridges get built, I guess. But there's a pretty serious trade-off.
Yes, there is very serious.
We're almost out of time. What do you see as the outlook for the near-term or even long-term future in terms of grand engineering as of the kind that we've been talking about, bridge building and so on, and the need for it on an ongoing basis?
Well, there's there's always a need for innovation, but we make a separation in the book that we wrote about this, the Power, Speed, and Form book, between radical innovation and normal innovation, or between breakthrough innovation and incremental, improving innovation.
Both of which you say are vital.
Yes, and breakthrough is what really makes the difference. That's what starts new industries. That's what starts on a new track, and the incremental follows that. But we have big industries, and we need incremental improvements in those industries for sure. I think in terms of the public works, I think I'm very optimistic about that, because I can see possibilities that's why we have these exhibitions in art museums. That's why we're trying to give a high-profile view as to what you could really build that would be a real improvement over what we're building nowadays. So I see much more possibility there, even though that sometimes takes longer, than in private industry, where we're locked into certain frameworks that are very hard to change, labor management frameworks. I mean, the automobile industry is just a perfect example of that problem. And to try to change that is not going to be quick and easy.
What is your hope for the future in terms of the engineers, the designers who will be building these great works of the future? I mean, you're in a good position to talk about that, since your classes at Princeton, I think you said, touched 60% of... No,
40%.
40. Oh, I got it backwards.
That's
but
all right.
Pretty impressive, though, for engineering courses.
That's right. And I think I'm very optimistic about that. And I get invited all the time to give public lectures. And I spent last spring, for example... I gave a major endowed lecture at Harvard and Yale, at Wellesley and MIT, and even the great engineering schools haven't really thought about these kinds of issues, I don't think. But the fact that they would have invited me to do this is an indication of something positive on the horizon. I only expect to be teaching for another 20 years, but when I want to get into triple digits, that's my goal.
Good.
Yeah.
We need you. I can't finish this without asking you about your two favorite bridges, or at least your favorite steel bridge and your favorite concrete bridge.
Well, the favorite concrete bridge is very easy to answer. That's the Salgina-Tobel Bridge in Switzerland, high up in the Alps. It was a bridge that was the basis of a design competition, a design-build competition, in which it was the least expensive of 19 different designs. So it was highly efficient and economical. It was a brand new type of form, which is now commonly used, called the hollow box in concrete. And its elegance is mostly accepted anywhere. It's been the subject of art museum exhibitions of all types. That's an easy one to do. It was the first concrete bridge to be made an International Historic Civil Engineering Landmark. In this country, the most important bridge is the George Washington Bridge, because it represented the biggest leap in span in all history. It almost doubled the longest spanning bridge before that bridge, and it is innovative in many different ways. The designer, Ottmar Ammann, was also Swiss, like Maillard, and the two of them had the same teacher for bridge design, and that's an important aspect, because I studied how that man taught, and that was a wonderful image of how one, I think, should be teaching these kinds of things to the next generation.
Thank you so much for taking a few minutes with us for this little podcast that we call the Transcast, and I know that your audience that's going to be hearing you in a few minutes here at USC is going to be thrilled. 48 years teaching at Princeton. I hope you get those 20 more you're looking forward to.
Yes, well, it's actually 50, but
no,
48 is right. 48 is right. I was a visiting lecturer for 2 years before that, so it's 50 years if you count that. Otherwise, it's 48 full-time professor. Yes.
Let's just call it 50 years.
I think it's a nice round number, yes.
David Billington is the Gordon Y.S. Wu Professor of Engineering in the Department of Civil and Environmental Engineering at Princeton University, only for the last half century or so. His honors and achievements and commendations are endless. You can find many of them online. What you can also find online, I am happy to say, are many of his books, including Power, Speed, and Form, Engineers in the Making of the 20th Century, and Big Dams of the New Deal Era, which I looked up on Amazon just last night, and they are very much available. And here is the Big Dams book he's holding up in front of us right now. Thank you again very much for joining us for Transcast.
Okay, Matt.
This has been a Metrans Transcast. Metrans is funded by the United States Department of Transportation and the California Department of Transportation, Caltrans. We hope you'll join us for the next edition of Transcast.